Welcome to our deep dive on data models.
Oh yeah, this will be fun.
You've sent us a chapter from Designing Data-Intensive Applications.
hmm
It explores how we structure data in this digital age,
hmm
and we are super excited to unpack it all with you. It's way more relevant than you might think.
Oh yeah?
This impacts everything from how our favorite apps work to how companies analyze trends.
Right. The way we model data is like foundational to computer science. It influences, how software is built and even how we approach problems, really.
Absolutely. The chapter digs into three main models:
Okay.
relational, document,
Yep.
and graph. Plus, it even hints at how these models are evolving and starting to blend.
Right.
I'm intrigued already. One of the first things that caught my eye was this idea of layering data models.
Okay.
It sounds kind of like an abstract art project to me.
It's more about managing complexity. So imagine a smartphone.
Okay.
You interact with apps without needing to know how the operating system works or the hardware underneath.
Right.
Like each layer hides the complexity below it, providing a simplified interface to the layer above.
So it's kind of like a chain of command for data, each
Yeah,
level with its own responsibilities.
exactly.
Okay.
Let's take a web application as an example.
Okay.
At the top, you have the app's code interacting with data,
Mm.
often structured as objects. This gets translated into a more general data model, like relational tables or JSON documents for storage.
Mhm.
And that storage layer itself is built upon even lower level representations of data, eventually ending up as electrical signals in the hardware.
Wow. So many layers.
Yeah.
But why is all this layering so important?
It allows for specialization and efficiency.
Hmm.
Developers working on the app don't need to worry about how data is physically stored.
Right.
And database administrators don't need to be concerned with the specifics of the application code.
Got it.
Yeah.
That makes sense. Speaking of databases, the chapter highlights the dominance of the relational model. It's amazing that something designed back in the 70s for transaction processing is still so prevalent today.
Yeah, it really speaks to the power and adaptability of the relational model.
Hmm.
Much of what we see on the web today is still powered by relational databases.
Mm-hmm.
Think about e-commerce sites with their product catalogs and customer orders, or online banking managing transactions and balances. These systems rely on the ability of relational databases to store and query structured data very efficiently.
So even with all the buzz about NoSQL, relational databases aren't going extinct anytime soon.
Not at all.
Okay.
No. The rise of NoSQL was more about having the right tool for the job. NoSQL databases emerged to handle specific needs that traditional relational databases weren't as well suited for. Think massive social networks needing to scale rapidly, or applications dealing with very dynamic data structures.
The chapter calls this polyglot persistence, right?
Wow.
Choosing the best database for each task. But doesn't that make things more complicated when you're deciding which database to use?
It does add complexity, but also offers more flexibility and better performance for specific needs.
Okay.
Like, for example, if you're building a large-scale social media platform where data is constantly changing and growing, a NoSQL database designed for flexibility and massive scaling might be the better choice.
So it's about carefully weighing the pros and cons of each type of database.
Absolutely. Choosing the right data model
Mhm.
impacts, development speed, the app's performance, even how easily you can analyze the data later on.
This makes me think of the object relational mismatch
Huh.
discussed in the chapter. It sounds like a real headache for developers.
It can be.
Yeah.
Object-oriented programming uses objects with, complex relationships, while relational databases rely on tables and rows. Trying to squeeze those objects into tables can be like fitting square pegs in round holes.
Yeah, the chapter uses the example of a LinkedIn profile to illustrate this. And I can see how a profile with all its sections, like experience, education, skills, and connections, could be tricky to represent in a traditional relational database.
Exactly. In a relational database, you'd likely need multiple tables with links between them to represent a LinkedIn profile, which can make retrieving and updating information more complex.
But in a document database, you could store the entire profile as a single JSON document, keeping all the information together in a way that's more natural to how we think about a profile.
Right. JSON, a simple way to represent data, is a great fit for document databases. This data locality makes it easier to retrieve and update profiles in one go.
This locality advantage seems like it would make things faster.
Yeah,
Are there any downsides to using JSON or document databases, though?
good question. While JSON is flexible, it doesn't inherently support specific data types, like dates and times, which can add some complexity for developers. And while not having a strict schema is great for flexibility, it can also lead to inconsistencies in the data if not carefully managed.
So it seems like there's always a trade-off when choosing a data model.
Yeah.
What about handling relationships between data? Like how would we deal with multiple work experiences in a LinkedIn profile?
That's a good example of a one-to-many relationship.
Okay.
In a relational database, you typically create a separate table for work experiences, linking it to the user's profile table.
Right.
This keeps things organized and allows for an unlimited number of work experiences.
Okay. And how would a document database handle that?
You could embed an array of work experiences within the user profile document itself.
Okay.
This keeps all the relevant information together, leveraging that data locality advantage we discussed earlier.
Okay, so both approaches seem to have their merits.
Right.
What are the key considerations when deciding between them?
It often comes down to the types of queries you need to perform and your performance requirements. If you frequently need to retrieve the entire profile with all its work experiences, the document database approach might be more efficient. But if you need to run complex queries involving filtering or joining data across multiple profiles and experiences, a relational database might be a better fit.
So it really depends on the specific needs of the application. What about more complex relationships like the many-to-many relationships the chapter discusses?
Yeah.
Those seem to pose a challenge for document databases.
You're right. Many-to-many relationships are where things get a bit trickier for document databases.
Okay.
They often lack robust support for joins, which are essential for efficiently querying these types of relationships.
Can you give me an example of a many-to-many relationship in the context of LinkedIn?
Sure. Imagine a feature where users can endorse each other for specific skills.
Okay.
This creates a many-to-many relationship between users and skills where multiple users can endorse the same skill and a user can be endorsed for multiple skills.
So how would you represent this in a relational database?
You would create a separate table for endorsements, linking it to both the user and skill tables. This allows you to easily query for all users who have endorsed a specific skill or all the skills a particular user has been endorsed for.
And what about in a document database?
It becomes more challenging. You could embed lists of skills within each user document and lists of users within each skill document. But this can lead to data duplication and potential inconsistencies if not carefully managed.
This reminds me of what the chapter said about the historical challenges with IMS and the hierarchical model. It almost sounds like document databases are facing a similar hurdle.
That's a great observation. The hierarchical model, popular decades ago, faced similar issues with many-to-many relationships, making it difficult to represent these relationships efficiently. Document databases, while advantageous in many scenarios, run into some of those same obstacles when it comes to more complex relationships.
So it seems like we've come full circle. Are graph databases the solution to this, like age-old problem of many-to-many relationships?
They definitely offer a very compelling solution. We'll delve into that more in the next part of our deep dive. Graph databases are specifically designed to model highly interconnected data, making them a natural fit for representing these complex relationships.
I'm already hooked. This is reminding me that even though technology changes rapidly, the fundamental challenges of data management persist.
Absolutely. And understanding the history of data models helps us appreciate the strengths and weaknesses of different approaches, which is essential for making informed decisions about choosing the best tools for the task.
That's a great place to wrap up part 1 of our deep dive on data models. Join us in part 2, where we'll explore the world of graph databases in more detail and see how they address those many-to-many relationship challenges. Welcome back to our deep dive on data models. In part 1, we explored relational and document databases, uncovering their strengths and weaknesses.
Right.
And we even stumbled upon a familiar challenge,
Yeah.
representing those complex many-to-many relationships. You hinted that graph databases might offer a more elegant solution. I'm excited to learn more.
Graph databases are fascinating. They excel at representing relationships, making them a natural fit for tackling those many-to-many scenarios that tripped up other models.
So instead of forcing everything into tables or documents, how do graph databases actually organize data?
Imagine a network of dots connected by lines.
Okay.
That's the essence of a graph database. The dots, called nodes, represent entities like people, products, or even concepts. The lines, called edges or relationships, show how those entities connect.
So it's a more visual way of thinking about data.
Exactly. And just like in those other models, the nodes and relationships can have properties,
Okay.
which are essentially pieces of information attached to them. Think of it like adding labels or tags to describe them further.
The chapter mentions property graphs. Is that a specific type of graph database?
Yes, property graphs are a common type where both nodes and relationships can have any number of properties. This makes them very flexible for representing different kinds of data.
Can you give me a concrete example? Let's stick with that LinkedIn profile we talked about earlier.
Sure. Say we want to show the relationship between a user and their skills.
Okay.
In a property graph, we'd create a node for the user, a node for each skill they have, and then connect them with a Haskell relationship.
And that relationship itself could have properties,
Right.
right?
Right.
Like the user's proficiency level for that skill or how many years of experience they have.
Precisely. We can capture not just the fact that they have the skill, but also the nuances of their experience with it. It's much more expressive than just listing user IDs and skill IDs in a table, wouldn't you say?
Definitely. It seems much more aligned with how we naturally think about connections.
Yeah.
But how do we actually search and extract information from a graph database?
Right.
The chapter mentions Cypher and Sparkle as specialized languages for this.
Those are two prominent query languages designed for working with graph data. They allow us to, traverse those relationships, find patterns, and extract insights that would be difficult to uncover with other models.
So instead of writing queries based on rows and columns, we're thinking in terms of nodes and connections.
Right. Let's imagine we want to find all users who are connected to someone who works at Google.
Okay.
In Cypher, the query might look something like this: match user.connected to friend that works at company name Google, return user.name.
So we're following a path through the graph. We start at a user node, then hop over to a friend using the connected to relationship. And finally, we check if that friend works at a company with the name Google.
Exactly. And if that path exists, we return the name of the original user. Cypher syntax makes it quite intuitive to express these kinds of traversals through the graph.
Okay, and what about Sparkle? How does it compare to Cypher?
Sparkle is also a declarative query language,
Oh.
but it's based on a model called triple stores, which are similar to property graphs, but use slightly different terminology.
The chapter mentioned that triple stores represent data as sets of 3 elements: subject, predicate, object.
Right. The subject is like the starting node, the predicate is the relationship, and the object is the ending node, or a value.
Okay.
For example, the triple, Alice, Nova Bob,
Hmm.
represents the relationship that Alice knows Bob.
Mm-hmm.
Sparkle provides a powerful way to query this triple-based data.
I'm seeing how this approach could be useful for complex data analysis. The chapter also briefly touched upon Datalog as another language for querying graph-like data.
Yeah.
What's its significance?
While not as widely used as Cypher or Sparkle, Datalog is important historically.
Okay.
It's a logic programming language that introduced concepts like recursive rules, which influenced the development of modern graph query languages.
So it's like a grandparent of graph query languages,
Yeah.
paving the way for their development.
You could say that. It laid some of the groundwork for expressing complex logic and inferring new information from existing data in graph-like structures.
Earlier, we talked about how relational and document databases have their pros and cons. I'm wondering, can we actually represent graph-like data using those other models, even if it's not ideal?
It's technically possible,
Okay.
but often leads to awkward and inefficient solutions. Remember how representing a LinkedIn profile with its multiple positions and skills required multiple tables and complex joins in a relational database?
Yes, it felt very cumbersome.
Trying to fit that same data into a relational model would be like trying to shove a square peg into a round hole.
Yeah.
It can be done, but it's clunky and doesn't take advantage of the strengths of either model.
So when would you specifically choose a graph database over those other options?
Graph databases truly shine when your data is highly interconnected, and you need to perform complex traversals or analyze relationships in depth. Think social networks, recommendation engines, fraud detection systems, any domain where understanding those connections is crucial.
It sounds like graph databases are especially valuable for discovering insights that wouldn't be apparent just by looking at individual data points in isolation.
Exactly. They allow us to uncover hidden patterns and relationships, leading to a deeper understanding of the data. We can answer questions like, what are the common interests of people who buy this product? Or how does information spread through a social network?
That's incredibly powerful. But before we move on, I'm curious about the practical aspects of graph databases.
Uh-huh.
Are there any limitations or performance considerations we should be aware of?
That's an important point to consider. While graph databases are optimized for traversing relationships, they can face challenges with very large data sets or extremely complex queries that involve a huge number of nodes and relationships.
So scalability could be a concern?
It can be. Performance depends on factors like the size of the graph, the complexity of the query, and how the database is implemented. Some graph databases are better suited for handling massive data sets than others.
It seems like there are always trade-offs to weigh when choosing a database. Is there anything else we should keep in mind when thinking about graph databases? Welcome back to the final part of our deep dive on data models. We've explored a fascinating range of approaches from traditional relational databases to the flexible world of document databases, and we even dove into the power of graph databases for understanding those, complex relationships. It's been quite a journey.
It really highlights how the field of data management is constantly evolving to address new challenges and unlock insights from ever-growing data sets.
Absolutely. One concept that's popped up throughout our conversation is data locality.
Uh-huh.
Earlier, we talked about how document databases can have a performance edge because they just naturally keep related data together.
Right.
Can you remind us why this matters?
Absolutely. Think of it like organizing your kitchen.
Uh,
If you're making a recipe and all the ingredients are within easy reach, you can work much faster and more efficiently than if you have to search for them all over the place.
yeah.
Similarly, when related data is stored close together in a database, retrieving it becomes much faster.
So it's about minimizing the time spent searching for and fetching the data we need.
Exactly. In a document database, an entire document, like that LinkedIn profile we discussed, is stored as a single unit.
Right.
Retrieving all that profile information requires just one read operation.
But in a relational database, the user's basic information might be in one table, their work experience in another, their skills in yet another.
Hmm.
That would require multiple reads and potentially complex joins to piece everything together, which sounds much slower.
Right. This separation of data can create performance bottlenecks,
Okay.
especially for applications that frequently need to access large amounts of related information.
So are document databases always the best choice when performance and data locality are top priorities?
Not necessarily. While document databases inherently promote data locality within documents, relational database systems have evolved to address these performance concerns as well.
Okay.
Techniques like clustered indexes or table interleaving allow related data from different tables to be physically stored closer together on disk,
Okay.
leading to faster retrieval times.
It sounds like different database models are starting to learn from each other and incorporate features that address their traditional weaknesses.
You're exactly right.
Yeah.
We're witnessing a convergence of features and capabilities across database models.
Mm-hmm.
Relational databases are embracing document-like features like JSON support,
Okay.
while document databases are adding relational-like capabilities such as joins.
It seems like the lines between these models are blurring, which makes choosing the right database even more nuanced. What's driving this trend towards convergence?
It's largely driven by the need to address an even wider range of use cases and provide developers with more flexible and powerful tools. As data continues to grow in volume and complexity, database systems need to adapt and evolve to keep pace.
Speaking of adapting and evolving, we've also talked about different query languages,
Yeah.
each with its own way of expressing how we want to search and extract data.
Right.
Are we seeing a similar trend toward convergence in the realm of query languages?
We are. There's a movement towards more declarative query languages,
Okay.
even in NoSQL databases.
Hmm.
Remember how we discussed MongoDB's aggregation pipeline?
Yes.
It offers a more declarative way to construct complex queries
Okay.
compared to the older MapReduce functionality.
And we saw how Cypher, specifically designed for graph databases, shares similarities with Spark Kernel,
Yeah.
which is used for querying triple stores.
That's a great observation.
Yeah.
It shows how the fundamental principles of data retrieval, regardless of the specific database model, are driving a common approach to querying declarative languages, which focus on specifying the desired results rather than the procedural steps, are becoming increasingly popular across different database paradigms.
Why is that shift towards declarative languages happening?
It simplifies development and unlocks performance gains.
Okay.
Declarative languages allow developers to focus on what data they want to retrieve
Right.
without needing to specify exactly how to do it step by step.
Okay.
This allows the database system to handle the optimization
Mm-hmm.
and potentially execute the query in parallel,
Right.
leading to faster results.
So it's like telling the database what you want and letting it figure out the best way to get it.
Precisely. This separation of concerns not only makes writing queries easier, but also empowers the database to use sophisticated techniques to retrieve the data as efficiently as possible.
So with all this talk about convergence and evolving features, what does the future hold for data models and database technology?
I believe we'll continue to see this trend of convergence,
Okay.
resulting in more versatile and powerful database systems. The lines between relational, document, and graph databases will become increasingly fluid,
Right.
offering developers a richer palette of options to match the specific needs of their applications.
So instead of a clear winner, we'll see more specialized tools coexisting and evolving together.
Exactly. Choosing the right data model will remain crucial, but it will become more about understanding the nuances of each approach and selecting the best fit for the task at hand.
Well, this deep dive has been incredibly illuminating. It's amazing to see how the field of data management is constantly pushing boundaries to keep pace with our, data-driven world.
It's a testament to the ingenuity of computer scientists and engineers who are constantly finding new ways to store, retrieve, and extract valuable insights from, ever-growing volumes of data.
And for you listening, I hope this deep dive has sparked a new awareness of the invisible structures that underpin our digital lives. Maybe you'll start noticing the different ways data is organized in the apps you use every day.
And if you're involved in building software, remember that choosing the right data model is a critical decision that can have a huge impact on your project's success. Think about the type of data you have, the relationships you need to represent, and how your application might evolve in the future.
Thank you for joining us on this data-driven adventure. Until next time, keep diving deep.